Online. When you are ready to begin. Our broadcast is now starting. All the
Okay, welcome everyone to today's class. And today we'll be looking at electric fields in materials, electric field in materials, and we'll be looking at electric field in matters. And that's what we'll be looking at today. The time we have, let's start with polarization. Polarization, and under polarization, we'll be looking at dielectrics, induced dipoles and polarability, alignments of polar molecules, polarization and susceptibility. So we'll be looking at them after the other. Now let's move ahead. When we talk about dielectric, they are conductors. The dielectric conductors charges freely to move. Their charges are free to move in the materials. Charges on this conductor are free to move on the material. And while for the insulator or the dielectrics, all charges are attached to specific atom or molecules. Now, stressing and rotating are the two principal mechanisms by which electric field can distort the charge distribution of dielectric atom or molecule. Now, the induced dipole and polarability. So this is the induced dipole and polarability. We have this as the neutral atom. We have this as the polarized atom, and we have the polarability. Now, for the induced dipole, P is equals to Q D, and which brings us to P, but P is Q by E, which brings us to that we can see on our screen right now. Let me go on the presentation mode. So now, a simple estimate, the field at distance D, the field at this distance, that's this D, the field at distance D from the center of a uniform charge sphere can be given by this formula. So this formula represents the field at a distance D from the center of a uniform sphere. Now, while at equilibrium, we arrived at this, at equilibrium, we arrived at this. Please note here that the V here is the volume of the atom, is the volume of the atom. Now, another thing I want us to know, in case a molecule, in the case of a molecule, it is more complex in the case of a molecule. So their polarization may not be isotropic. Their polarization may not be isotropic. So generally, I have it as this for generally we use this for molecules. Then the most general linear, then you can also make it to be y alpha polarizability. Then put it in the three coordinate in y x. We have this p of course a of alpha x of x, e of x, x of y, e of y plus alpha e of z. The same thing you read for p y or p of y. So now alpha ij depends on the orientation of the axis you choose. So the alpha ij or alpha subscript ij depends on the orientation of the axis you are choosing or you want to use. it's possible to select as a such alpha ij is equal to where I is not equal to j. It's possible for you to alignment of polar molecules. Polar molecules have built-in dipole moment. Polar molecules has built-in dipole moment. If you look at this diagram, this is applied electric field, a uniformly applied electric field, a uniformly applied electric field. So now this is for the formula we derive from it. Torque gives us this, and we're able to use this as a formula. If the applied field is non-uniform, then the total force is not zero. They will have this, that is Q interchange in E, Q interchange in E. So we can also open it up to be this for short dipole. We can use this bar F is equals to bar of bracket open and close, bar of P dot bar of V multiplied by bar E, that is the electric field. Polarization and susceptibility. The polarization of a polarized dielectric. Now we have it as this, and this time, and when you try to represent it, P is equal to x naught x of E dot E, where x of E is electric susceptibility tensor, and if you put it in your x, y, z, we have it at this. For linear dielectric, we use this for linear dielectric, so same thing as we have here, where x of E is susceptibility of the and the field of polarized objects. When we look at the field of polarized objects, the bound charges, then physical interpretation of bound charges and the field inside dielectric. So now let's look at the bound charges. Now bound charges divide the materials into infinitesimal and sum up So this is bound charges divide the materials into infinitesimal and sum up. So for bound charges, surface charge is given as this, while volume charge is given as minus bar v dot p. So it's given as this. So we have this for that. Now, for with this can also be perfectly genuine accommodation of charge uniformly distributed dipole. So dipole moments can be given as this P into A B, which is equals to Q D, and making Q the subject, we have Q is equals P A, P mod or P dot A, and when you have OB is equal to Q all over A, which is equals P. So that is that. And for a uniform polarization oblicate, we have this. We have this for that. Then sorry, we have this. Then for non-uniform, we have this. And why for use the we use this in Gauss law also works in the presence of dielectric. So the total charge density is equals density B plus density F. So and this is the bond and this is the free. This bond and density free. So and we could have Gauss as, which implies that V is equals for density free, which is equals density free. So in the can be written as V dot D, but D is equals to density free, and can also be but D equals straight the E plus just this electric displacement. So we could have it as this short example. A long wire with linear charge alpha is converted with insulation of a radius a. Find the electric displacement. Find the electrical displacement. Now let's look at it this way. Now from our previous section, you could find this formula after. This is the formula we are trying to in now. So we bring in there and have our b into 2 pi rl, which is equals alpha l. So by then is equals alpha all over, sorry, lambda all over 2 pi r multiplied by the r. So we do not know the e, we don't know this. So and we need to know this one too. So outside we have this formula for the e to get our d, and which gives us lambda all over 2 pi e epsilon multiplied by this. So for r is greater than cap r. So for deceptive parallel, we have it as this. And since v multiplied by a is equal 0, so the solution is unique. The solution is unique. So Helmholtz theorem, this is for Helmholtz theorem, and he was able to prove this, that well, v multiplied by p is not always 0. He was always able to tell us that this multiplied by this is not always 0. Yeah, it's no potential for D. In general, there's no potential for D. There's no potential for D. For linear dielectrics, we have it as this, and where Xe is electric susceptibility. And when we go further, we have the permittivity, which is this, and we have the permittivity of free space, epsilon 0, the permittivity of free space into 1 plus x of E. And we said the x of E is electric susceptibility. So 1 plus electric susceptibility. So the dielectric constant or relative permittivity now is equals to 1 plus electric susceptibility, which is equals to permittivity all over permittivity of free space. So when we impute this, we have this. But let's look at this also. A metal sphere of radius has a charge Q. Of radius has a charge Q. If you could see my mouse, this is the Q. It is surrounded by a linear dielectric material of permittivity. Linear dielectric material of permittivity. Find the potential at the center and bound charges of the medium. That is, we have to look for this. So I'm sorry. So we go with this. We don't know this center. We don't know anything, the potential at the center. So we don't know this. So and to get that, we go by using E this and is equal to this, which equals 0 for r is less than alpha or less than, yeah, and this brings us this again for the same thing. So now for the E, we will now have the Q all over 4 pi s permittivity r squared r. So for B is less than r less than A, and which also gives us this. And therefore now the center we don't know about is giving us this, and we obtain our value as this here. So we also have this, and the density is giving us this at r is equal to A, this at r is equal to B. Look at another one before we run further. A parallel plate capacitor is filled with an insulating material of dielectric content. What is the effect of dielectric on capacitance? Without dielectric, there is V vac is equal to E dot D. The dielectric reduces the E to E all over permittivity R or dielectric constant. So V dot the E, which is equals to E all over permittivity constant or dielectric constant, B. So the capacitance is Q all over V. So we now have it as okay. Let's look at boundary condition. Boundary conditions. And this is field normal to substance. Field normal to substance. Sorry. So field normal to substance. Let's quickly go over the boundaries. Let's quickly go over the boundary conditions one more time. One after the other. Okay. To evaporate his head. Boundary conditions. Please just give me a minute to rectify this out. A minute, please. Thank you. So, sorry about that. Now, this is another example. So, because of time, we will not be treating this with this. Yeah. Then this is for for to surface, field normal to surface, then field parallel to surface, and we have the formula as this. In the case of the above, conditions become D above minus D below, and which gives us parallel P parallel above minus P parallel below, and we'll have V above is equals to V below. So now that electric sphere is in a uniform electric field. Find the electric inside the sphere. So we go. I know some of us might be confused with these formulas we are bringing up, but don't worry. We'll be looking at some calculations. As if not today, if time permits, so if not today, maybe next week we'll be looking at some calculations. I will advise everyone, let your calculator be by your side. For inside the sphere, we have this, and for outside the sphere, we use this. And for boundary condition one, then we go with this. So also we have it here, the boundary condition for one, or for I, we have it as this, and for two, we use this, and so on. Energy in a dielectric system. And the energy of a charge capacitor is given by this, W equals 1 over 2 CV squared. That's the energy of a charge capacitor. If the capacitor is filled with a dielectric, so we have it as this. If the capacitor is filled with a dielectric, so the stored energy should increase by the same factor. And energy stored in any electrostatic system, as in a vacuum, is given as this. With linear dielectric, we have this for linear dielectric, which suggests the energy in the dielectric is given as this, or is equal to this. Suppose we are gradually building up charges in a dielectric medium. So for linear dielectric, we use this, and this is what we derive from this. Forces on dielectric with Q constant. So we have the W is equals F of EX to X to dx, sorry, and we compute with this. Now is what we do. And if V is kept constant in this, if V is kept constant, then we use this. The reason is to keep the constant. The battery must do work so that there's no taking account to have to do everything not with correct or sign direction. Now in media, electrostatic in media, the conductivity depends on temperature and frequency. The conductivity of electrostatic materials in media may be classified in terms of their conductivity as conductors, non-conductors. For conductors, the conductivity usually depends on temperature and frequency. They are materials with high conductivity, and a matter with high conductivity is a metal. You and me know that metal conduct electricity very well. It's a conductor of electricity. A material with low conductivity is insulator, and a material with conductivity between is a semiconductor. That is a connectivity. A material, a conductivity, whereby conductivity is in between the material is semiconductor. If a material exhibits infinite conductivity at T is equals 0 degree K, is a superconductor. For insulators, that they're electric material, D is equals permittivity E applies, so it's homogeneous if permittivity does not change from point, or if electric constant does not change from point to point. It's isotropic of that electric constant not change with direction, and linear if it does not change with light, electromagnetic field or electric field. Polarization and electric flux density. Unlike the free charges in a vacuum, which produces an electrostatic field, the dielectric medium does not have any free charges. The dielectric medium does not have any free charges. So in the absence of an external electric field, the electron form a symmetrical cloud around the nucleus, with the center coincide with the nucleus. So this is what you are seeing here. The electron still when an external electric field is applied, when an external electric field is applied, of the electron cloud will move away from the nucleus, which is polarization. The polarized atoms or molecules is represented by an electric pole. Now the displacements are limited by strong rotating force set up by charge configuration in the molecule. So this polarization gives rise to an electric field in opposite direction to the applied field. The state of polarization is described by the vector of polarization. So, and this is the SI unit coulomb per meter square. It is defined as the electric dipole moment per unit volume. The electric dipole moment per unit volume. So this is that, and the uniform polarization. This is for uniform polarization. The material is equivalent to a free space, that is space with surface and volume polarized charges or bounded charges. So this is for non-polarization. We have it as this. So let us have a medium in space containing both free and bounded charges. The electric field intensity due to both types can be calculated as using this, and where density and density B are the free and bounded charges respectively in coulomb per meter cube joule. The mixed quantity is a definition for electric influx density. For electric influx density. So we they have them as this. General differential form of Gauss law is given as this, and general integral form of Gauss law we also have it as this. The source of D, or the source of electric flux density, is the true free charge due to this equation here. Why the polarization vector is stirring up the D. The source of E is the total charges through free charge plus polarization charge due to this also. So those are the, now we can define the electric flux density and its relation with electric field intensity as this. So, and why this is called permittivity of dielectric. Now, S of E is a dimensionless quantity called electric susceptibility. It measures how susceptible or sensitive a given dielectric is to electric field. So we have this. This is given. It's telling us that relative permittivity. A basic equation of electrostatic field in form, we have it as this, and for integral form, we have it as this. So these are the basic equation for electrostatic field in a material media. So for what we've spoken so far, we could see it as this here. Then the boundary conditions of electrostatic fields. So boundary conditions of electrostatic, the boundary conditions, surfaces that dividing the space regions of different permittivity and carrying a surface distribution of charges causes the line of this, causes the line A to D to be discontinuous, and hence we call them boundaries, causes the line to be discontinuous. So in other words, when a line is discontinuous, we call them boundaries. We call them boundaries, or they are known as boundaries. Now, capacitance. An idealized circuit element for electrostatic energy stored in the system and is characterized by Coulomb's voltage law, which says V is not proportional to Q. So loads, and that gives us as V is equal to bracket opener close 1 all over C multiplied by Q. So any two conducting bodies, regardless of their shape and sizes, when separated by an insulating, that is dielectric medium, forms a capacitor. Now, what it's saying is when two conducting bodies, regardless of their shapes, are separated by an insulation, then the capacitor, they form a capacitor. So let's by diagram you can see these bodies, um these two body or conducting bodies separated, so they form a capacitor. They form a capacitor. This conductor one, conductor two. So this carries the positive charge, while this carries the negative charge. And capacitor is measured in microfarad. So this is example of a parallel plate capacitor. We have the dielectric, which is the insulator, and the conducting plate. This the conducting plate. So the insulator is in between them. Then from the definition of voltage, we have it as V is equals minus integral 0 to D E dot dl, which is equals minus 0 integral 0 to D into minus sigma E dot sigma dx, which is E D, taking into account that the capacity is given by these equations here. So example, capacitance of coaxial line. Capacitance of coaxial line. You can see that here, coaxial line, and we have the inner conductor, the dielectric material, the outer conductor. So you have them. Now the electric field is described by A is less than R less than B, and is given by this formula here. The voltage between inner and outer conductor is the voltage between the inner and outer conductor is given by this formula here. Then the capacity is then given by this. So if you are asked to calculate the voltage between the inner and outer capacitor, so its formula is given by this. Now, electrostatic boundary value problem. So let's look at, now we saw that E was determined by Coulomb's law or Gauss' law when charge distribution is known, or E is equals minus bar V, where potential um, potential V is known throughout the region. In most practical application, neither the charge distribution nor the potential distribution is known. So in here we're going to be talking about practical electrostatic problems that are considered when only electrostatic conditions, that the charge and potentials at some boundaries are known, and some boundaries are known. So now let's go with this. There are easily, this is a Poisson and Laplace equation. So they are easily derived. They are easily derived from Gauss' law. So we have them as this, and this is for an inhomogeneous medium, and this is for homogeneous medium, that is Poisson's equation. So and for charge-free region we have this for charge-free region, and for Laplace equation we have it as this. Now the Cartesian with Laplace equation, the Cartesian will have the spell V all over this. Now we get this. Then the cylindrical, for cylindrical, we obtain this is equal to 0, and for spherical, we have this as equal to 0. Uniqueness theorem. In uniqueness theorem, there are several methods of solving a given problem: analytical, graphical, numerical, experimental, etc. Now the question is, if a solution of Laplace equation satisfies a given set of boundary conditions, is this the only possible solution? The answer is yes. There's only one solution and it is unique. Now this is uniqueness theorem. If a solution of Laplace equation can be found that satisfies the boundary equation, then the solution is unique. It satisfies it because it satisfies it. Now let's take this as, sorry. Sorry. Okay. Okay, let's just do it. Okay, let's take this example. Two conducting cone theta is equals pi 10 and theta is equals pi all over 6 of infinite extent are separated by an infinitesimal gap is equals 0. If V is equals theta, if V into theta minus pi over 10 is equals 0, and V into theta equals pi over 6 is equals 50 volts, find V and E between the cone. V and E between the cone. So these are the gaps. So find V and E between the cone. So let's look at it. So since V depends on equation is spherical. So since V depends on theta, Laplace equation is spherical. The coordinate now becomes this. We have this as the coordinate. And since R is equal 0 and theta is equal 0, now pi are excluded. We can multiply by R squared sine theta base. Integrating once gives us this, and integrating result, then we have this. We can obtain our value as this. applying boundary condition to determine the integration constant. So we have this, and we are able to, so it continues that taking theta 1 equals pi all over 10, theta 2 equals pi all over 6, and V, the voltage, equals 50, gives us, when we input these values into the formula, then we are able to have this. And going further, we divide it by r sine theta multiplied by alpha theta, then by voltage meter, then we have this as our answer here. We have this. Resistance and capacitance. Resistance and capacitance. Resistance and capacitance. For conductors with uniform cross section, the resistance is this. R is equal to L all over OX. And if the cross section of the conductor is not uniform, resistance is obtained from this, which is R is equals B all over I, which is into integral E dot dl all over integral rho E dot dx. The resistance R or conductance G is equals 1 all over R of a conducting material can be found by the following steps. 1. Choose a suitable coordinate system. 2. Assume V0 as the potential difference between conductor terminals. And 3. Solve Laplace equation to obtain V, then determine the E from this formula and find I from this. Finally, obtain R as V0 all over I. To have capacitance, we must have two or more conductors carrying equal but opposite charges. That is to have capacitance. So if you see my diagram, we have two conductors carrying equal and opposite charges. Equal and opposite charges. So their charges are opposite. The conductors may be separated by free space or dielectric. Maybe this is a free space. So the conductors are maintained at a potential difference. So this is it. And note that E is always normal to conducting surface. The capacitance C of the capacitor is defined as the ratio of the magnitude of the charge on one of the plates to potential difference between them. So this is the capacitance of a capacitor defined as this. Then C, we obtain C for any two conductor capacitors by either, we can obtain C by either assuming Q and the V in terms of Q involves this law, or V and determine Q in terms of V involves Laplace equation. So let's check the methods we can involves the following. Method 1 involves choose a suitable coordinate system and let the two conducting charges plus Q and minus Q. And 3. Determine E using Coulomb's or Gauss law and find it from this equation. V now equals minus integral E dI or dL. And finally, obtain C. From using this, you obtain C. C is equals Q all over V. This is for some of us that don't know capacitor. This is capacitor. This is capacitor. This in electronics. You see it most time in electronics. This is a picture of a capacitor. These are 50 microfarad, like what the technician will say. So it's actually microfarad. Storing charges capacitor. A capacitor consists of two conductors. A capacitor consists of two conductors of any placed near one another without touching. So of any shape placed near one another without touching. If you can see my screen, you see these two shapes, they are not touching each other without. It's common to fill up the region between these two conductors with an insulating material. So this blue space you are seeing is a dielectric insulating material. called the electric. We charge this we charge these capacitors, we charge these plates with opposing charges, the plates with opposing charges. So we charge the plates with opposing charges. So this is for capacitance. We have this, or we use this. This is Gauss Coulomb's law in terms of Q. So we use, and for resistance we use these formulas. Suppose each plate has an area S and the plates are separated by distance d. Assume plates 1 and 2 carry uniformly distributed charges plus Q and minus Q. And thus for a parallel plate. So now suppose we have each plate has an area of X. So we use this. Okay, here said each one has an area of X. The whole of this area is X. The whole of this for this one is X. So the energy stored in capacitor is given by this. This is the energy stored in a capacitor. So we have coaxial capacitor. For coaxial capacitor, the plastic jacket, the dielectric insulator, the metallic shield, and the center core. So the capacitance of a coaxial cylinder is given by this formula, that is C is equals Q all over V, which is equals 2 pi S long, or primitivity L all over ln B all over A, for capacitance of a coaxial cylinder. So, and for capacitance of a spherical capacitor, we have this capacitance of a spherical capacitor. We have this formula, which is C is equals Q all over V equal 4 pi permittivity all over 1 over A minus 1 all over B. That is for spherical capacitor. Now, series and parallel. If two capacitors with capacitance C1 and C2 are in series, then they have same charge on them. The total capacitance is given as this. When for capacitors in series, if they have the same charges, 1 all over C is equals 1 all over C1 plus 1 all over C2, or C is equals C1 C2 all over C1 plus C2. Now, if the capacitors are in parallel and have same voltage across them, then we have this formula: C is equals C1 plus C2. This is this we are saying, if you can see, remember, is a capacitor connected in series. Capacitor connected in series, and this is capacitor in parallel. Um, Now let's check on this. A metal bar of conductivity is bent to form a float 90-degree sector of inner radius A, outer radius B, and thickness T, as shown in the figure. This is Z. Now show that the resistance of the bar between the vertical curved surfaces at R is equals A, and R is equals B is this. Then B is the resistance between the two horizontal surfaces at Z equals 0 and Z equals T is this. So this is what we asked to show. But for the sake of our time, I think we have 5 minutes to go. We might not be able to start going through this solution, but I promise you in our next class, we're going to do calculation, purely calculation. So please, let's try and have our calculators by our side next week, because you'll be doing the computation and concluding the solving, you'll be doing the computation and concluding the solving. So this talk will be forwarded to admin, and which admin will forward back to you as soon as we are through, or we will have the materials. Admin forwards the materials to you. So I want to say thank you for listening to me again. We're not taking any assignment, and like last lecture last week, most of us did not turn in assignments. It's not proper. We should try and turn in our assignments. It's very, very important that everyone turn in their assignments. So let's try and turn in our. So I want to thank you again for listening to me. I'll say till then, please stay safe. Thank you.